8 people in total, 9.
In 5 years' time, I should be used to this system.
Oh. All right, guys. Good luck. Enjoy.
Right, guys. Where were we 2 weeks ago in the material? Silence. Okay, let's have a brief recap on the image process. Let's go back a month. First things we looked at were single pixel operators. They are basically arithmetical functions on individual pixel values. Now, so far we've concentrated on grey level images. Color is a little bit more complicated, but the principle is the same. In fact, with color, you wouldn't normalize on the red, green, and the blue. You would try and enhance on the intensity rather than the hue and the saturation. So RGB is not a good format for color processing. Right, back to the single pixels. The two main operators were add, where you are simply adding a value to a pixel value. So the output pixel Bij is equal to Aij plus K. And of course, K can be negative. When I say add, it also includes subtraction. Adding is making the image brighter. Subtraction is making the image darker. But you have to clip the values, because in an image system, if you go to maximum white and you try and add something to it, it will overflow. And supposing I've got for 4 bits, supposing I've got 1111, which is 15, which is the brightest 4-bit value, absolute white, and I add 1 to it, I get 16. The system has 4 bits resolution. It will look at the least 4 significant bits, and it will see a totally black pixel. And so it will completely distort the image unless you clip it. And the conditions are Aij equals W for Aij plus K is greater than W, and it is 0 for Aij plus K is less than 0. So that's the add. The multiply is Bij, the output pixel, equals Aij times K, as you would expect from multiply. And the limits are going to be W for Aij times K is greater than W, and this will be 0 for Aij times K is less than 0. So it clips at black and white. Now, taking those two simple operations, we can enhance images. And to enhance an image, I showed you the picture of that guy. I don't think I've brought it this time. But if you want to enhance the whole image, a process of shifting and multiplying can redistribute the pixels proportionally across the whole intensity range. So if you were to take an image and we get the histogram, and the histogram is simply the record of pixels and their number of pixels at each intensity. In the exam, if you have a question like this, it will be 4 bits. So you will have 16 intensities, 0 to 15. And you go through the image, count up how many pixels at 0, how many pixels at 1. So we get the number versus the intensity. And it will be a discrete histogram. Sometimes they are drawn as continuous functions for speed, but we might have something like that, where that is 0 and that is W. Now, to enhance that, we do a shift, identifying G min, which is there, and G max. And the first thing we do is shift the histogram with K equals minus G min. So the whole thing is shifted down. This goes to 0, and this will go to G max minus G min. Having got that, so the first thing is shift. The second operation is multiply. And the shift is going to be K equals minus G min. And then you multiply. And the multiply constant is going to be W over G max minus G min. And so we end up with a histogram which looks exactly the same shape but spread from naught and offset the naught because it won't then correspond with the vertical axis. And that will be W. That goes to naught, that goes to W, and we've got all the values proportionately in between. Then what do we do? Pixel update table. Don't lose sight of the whole point of this is to produce an image of better quality. And in the exam, I have sometimes seen people get up to that point and say, that's the answer. So that's not a very interesting picture. So the final step is pixel update. How do you do that? You find the pixel values of the darkest in the original image. Where does it go to? Naught. This one, that value, updated to that value. And of course, the top one updated to white. And then you scan through the original image. You've got the pixel update table. You can read the input pixel, and you know what the output pixel value from that table is going to be. And you get your enhanced image. Then, of course, the next thing is selective normalization, selective enhancement. You might want to look at the very dark area of the image. So maybe we would take a region, maybe there to there, to enhance. And we would assume that the rest can be whited out because you're looking to see who that person is lurking in the shadows in the dark when the street light is down the road. And on the normal image, it looks pretty murky, you can't see the person. But if you enhance the black region, forget about the white region, then you can get some details out. And it goes the other way around. If you want details on the white region, somebody working in an office with a computer, and there's a screen, and you want to see what's on the screen, you can enhance the white region and black out the rest. And so that's useful for many applications. Right, so that was the monadic. The dyadic operators, 2 pixel operators. I won't go through all of them because you should have notes for them. Picture add. As an example. And let's take Cij, the output pixel, equals Aij plus Bij. But it has to be normalized because the right-hand side has a potential of 2W. In the case of Aij being W and Bij being W, adding them together gives you 2W, and your imaging system has only range 0 to W. So the obvious correction factor, of course, is divide by 2. And for subtract, it is going to be Cij equals Aij minus Bij. And what's the correction factor for subtract?
Plus W.
Plus W. And the whole thing is divided by 2. Right, so that's dyadic, and they're really used for arty-farty sort of tarting up images and special effects. But they can have some use in real image processing. Right, then we came on to the window operators. And the window operator was, the first one was the low pass filter, which is a 3x3 window that scans the image. And what are the coordinates of the low pass filter? You have forgotten. So work it out from first principles. Low pass filtering is smoothing, it's averaging. So if you want to average all the pixels, first thing you do is add them all up. The easiest way to add them up without changing their values are to have coordinates of 1. 3x3 window, you can apply it twice and get a bigger effect. or you could devise a 5 by 5 window by superimposing that in 4 positions and adding up the weights and do a single pass. I'd stick with the 3 by 3, and if you want a double filtering, use it twice. Right, what's the problem with that? Okay, yep.
End up with a smaller outer picture.
Yes, remember that. You will lose the edge, the tops and the bottoms, because the output pixel is corresponding to the center of the window. And in an exam, you might, if it comes up, get a 5 by 5 input image, expect a 3 by 3 answer after filtering, which is a dramatic reduction in size, but that's such a silly example. In practice, you're using 4,000 by 4,000, and your filtered image will be 3,998 by 3,998 pixels. And I challenge any of you to tell the difference, unless you've got supersonic eyes. Right, another problem. What are the limits of that? Okay, it's looking at a black region of image. What's the output? Naught. It's looking at an absolute white part of the image. What's the output? W plus W plus W. Is that a clue? It's going to be 9W. So after filtering, you have a range of 0 to 9W. Completely outside the range of the image processing hardware. What do you do? After filtering, you divide by 9. And that's where I think we were up to in the last lecture, yes?
Yeah.
Right. Okay, if there is low pass filtering, what else do you think there is? High pass filtering, good. And high pass filtering, the simplest high pass filter. And the window operator is 3 by 3 again. The output is physically corresponding to the center pixel of the filter. And the weights are, in the simplest one, -1, -1, -1, -1, -1, -1, -1, -1, -1, plus 8. And that is going to peak the value of the center pixel and subtracting the surround. So it's going to enhance the difference between the pixels. So there we are. We correlate that with an image. Right. What is the limits of the output for that window operator? What is the lowest value I can possibly get?
-8.
Minus
-8.
-8W.
Yeah.
Yeah. What is the image to give that? This is the image. And it is going to be, let's have white, 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 black. This is grey, not binary. So the blank squares are white as they look, and the black squares are black. So in the case of 4-bit resolution image, the whites would be 15 in decimal value, and the black would be 0. We would have -W, -2W, 3, 4, 5, 6, 7, 8. That's your -8W. The upper limit,
8W.
plus 8W. And that would be the image. all the outer one's black, and the inner one is white. That is weighted 8. All the minuses are black and naught, so it doesn't matter, so we end up with plus 8W. So it's now got a range of much greater than the image processing system. What might you think the normalization should be to bring that into the range 0 to W? Hello there. Had a good breakfast? Divide by 8. That'll take it to minus W to plus W. Well, I've got to get the bottom, the least possible value, to 0. And at the moment, the least possible value is minus 8W.
Would you divide by 16 and add W?
You could. Now, I don't want you to write this down, because it would appear that the normalization is going to be, let's call it a Cij equals 8. No, let's do it that way. Shift by 8W and divide by 16. And that would indeed bring it into 0 to W range. But having written that down, in practice, no. Why? Because these pixel values, perceptually, they're not important. You're dealing with single pixels at this stage. And this situation here, where you've got a black pixel on a white background, here we've got a perfectly real life example. This person here wearing a nice white jumper, and I put deliberately 1 pixel black. Whoops, sorry. Perceptually unimportant. You can't see it. And the other one, black surface with a white pixel in the middle. Well, it's likely to be that guy there. Look, I can see a real world example of this. Look, there's a lovely black jumper. It's like a dandruff. You don't want people to see that, do you? So both of those are perceptually totally unimportant. And forget about the black dot and the bit of dandruff. Those pictures are most likely to be due to faults on your camera, where the system is looking at a white region and the pixel is duff. It's open circuit or short circuit. And remember, you've got 16 million cells on the real image. And the other one could be, it's looking at a black region such as this, and the pixel in the middle is stuck at naught or whatever. So those are not significant. And if you normalize those to those limits, the important information, which is the face or the scene you're looking at, would be compressed into a very small region of image space. It would be no good at all. So, correction. We don't use arithmetical shifting. One, having done the raw filtering, the ranges go between -8 and -8W and +8W. Having done that, obtain the histogram. Of the filtered image. And the histogram is going to look something like this. It is going to go from -8W, naught is going to be in the middle, and plus 8W there. And we may well have a few dodgy pixels giving minus 8W. We may have one or two sticking there. And then in between will be your histogram values. Right. Having done that, we now want to contract that to 0 to W, but we don't want to use the minus 8 and the plus 8 as the limits. So what you've got to estimate is a reasonable G min, which will not be at the bottom. Let's say call that G min. And let's decide that that's G max. You ignore the outliers. Having got G min and G max, then what do you do? It's a histogram. Normal enhancement, shift G min to 0 and shift or multiply. It will be G max and that will then reduce the histogram to 0 to W. So this value here, call that A, is going to go to there, and call that B, is going to be W, and everything in between. Having got that, we've got the data between 0 and W. What's the next step? There's a clue. Look up table. I'm looking up. See, I'm looking up. Oh dear, too early in the morning for jokes. So, look up table. Or pixel update. So, don't normalize to the raw limits after filtering if you're doing high pass filtering. There is another problem with the high pass filter. Background. Oh, these stupid pens. Nibs disappeared. Oh. Brunel University, you have crap equipment. Right. Supposing the operator is looking at a constant region. This is image. And supposing the image is all zeros. Obvious question, what's the output going to be? Zero. Supposing it's looking at a mid-range grey background. 7, 7, 7, 7, 7, 7, 7, 7, 7. What is the output pixel going to be? Come on.
0.
0, yes. And supposing it's going to be looking at an absolute white region. It's going to be 15 or W. What's the output going to be?
0.
0. What do you conclude from high-pass filtering from that little test? A high-pass filtered image, the constant areas, the background, the black here, the white there, the in-between greys, what's it going to be?
0.
0. The background after filtering will be black. So you're losing the background. So in terms of enhancing an image to give more contrast, okay, you're enhancing the edges. It can be used as an edge detector, but you're losing the background. Now, if this was enhancing an old film or whatever, and you wanted to retain the background, it's black. So if we want to retain some form of the background, anybody got a suggestion what we might need to do? Another operation. Use the 2-pixel operator, add the original pixel. It will restore some of the background information. You'll lose some of the contrast enhancement. It's a compromise, but if you want background information, actually use it as a picture rather than locating areas for edge detection. If you add the original image, and so the equation for that is going to be Cij equals Aij plus Bij divided by 2. And this will be the original. This is the filter pixel. So that is the simplest low-pass filter. You will come across, if you do some reading, this is a high-pass filter. You will come across other high-pass filters. I just mentioned one in passing. It's sometimes called the Laplacian. And the Laplacian high-pass filter, again, a 3x3 window. The objective of this is to weight the horizontal and vertical pixels more than the diagonals, because the diagonal physically is further away from the center pixel than the top and the bottom. √2 factor. Remember that original error in measuring on square pixels you can't eliminate. If you're moving 1 pixel diagonal, you are moving √2 distance. If you're moving up and down 1 pixel, it's 1. Built-in 40% error. And you can go to huge resolution, it never changes. Now the Laplacian has -2, -2, -2, -2 to give more weights to the nearer pixels, -1, -1, -1, -1. And again, it's a balanced operator. So looking at constant regions, we get 0 out. So the center pixel weight is positive, and it is the sum of all the neighboring pixels. So it will be -1, -2, 3, 4, 6, 7, 8, 9, 10, 11, 12. It will be +12. And of course, we could go slightly more accurate. We could have 3s, 2, 2, 2, and I think it's 24 in the middle. Same principle, supposedly slightly better, but really not much difference between them. So that's the high pass filter. Right. How are we doing for time? I've got plenty of time. I'd better just mention something about image equalization. Different from normalization. Equalization, we're going to do something which is equalizing something about the image. And most or some books will describe equalization as a strategy, a transform that produces a flat histogram. So an equalized histogram would be a histogram where all the entries are the same. And this was first proposed for equalization, but now we're using so much CCTV and it's used for legal purposes. They suddenly realized that if you equalize the histogram completely, you are tampering with the image. Because if I had a picture, a histogram, a very simple example, that looks like that, and I were to equalize that, it would give me, or would possibly give me, this one will be reduced, this one will be enhanced, it would give me that. And of course, you've changed some pixel values. So if you were finding yourself in a bit of bother with CCTV imagery and it's been equalized, you can say, hey, that's been tampered with. That's not my picture, that's not my face. And also, having done that, there is no way back to this one. So it's a lossy normalization. So that the idea of a completely flat histogram is not used these days. But what we can use is equalization in bands. And I will take a very simple example. And supposing we have the histogram, I'll draw it as an analog function to save time. Supposing I have a distribution like that. This is number, this is intensity. We need to detect, as usual, G max and G min. And this is going to be two bands in this example. So G min is going to be there. This is going to be G max, normal. But we also need to detect G 50%, which is the middle grey level pixel. It's the point at which 50% of the pixels are darker and 50% of the pixels are brighter. And this can give us two bands. This will be my band A, and this will be my band B. Now, the method to equalize. For band A, let's extract band A from the histogram, and it's going to look something like this. And from that, we've got our G min, and here we've got G 50%. Now, having got that, shift to 0, and that is going to be K equals minus G min. Right. And the second operation is multiply. And K for the multiplication is going to be taking the shifted value. Perhaps I should draw the shifted value. This is going to be 0. A is going to come around something like that. This is 0 now. and this is going to be G 50% minus G min. And the multiplication factor, we now want to take that band over an equal range of pixels. And for two bands, if we're going to have equal populations, the bottom 50% is going to be between 0 and W over 2, the midway intensity point. So we now want to normalize that to 0 to W over 2, and the multiplication factor is going to be K equals W over 2 divided by G 50% minus G min. So in other words, having done that, this is band A, it's going to be distributed between 0 and W over 2. And we're going to get that, move that over. Oh, so W over 2 there. And so it's going to look something like this. Spread out. So that's band 1. We now take band B. Here's band B over here. So for band B, and let's draw it now. It was originally at G 50%. It's going to go up there and down there, which was G max. And this is B. Now, if I start multiplying with band B, starting from G 50%, supposing I multiplied it by 2, the whole thing shifts right out of range. You lose that information. So what you've got to do, first of all, is not operate in the intensity range G 50% to G max. You've got to take the G 50% to 0. And so K, therefore, is going to be minus G 50%. And having done that, the histogram is going to look something like this. And this is now going to be 0, and this is going to be G max minus G 50%. Next step. Spread that now over half the intensity range. And we're at the bottom, so we're going to spread it between 0 and W over 2. And the K is going to be, it is going to be W over 2 divided by G max minus G 50%. And the resulting histogram will be naught to W, and it's band B. It looks something like this. And it's going to go down there, and this is W over 2. That's band B. So we've now got band B spread over half the intensity range. But it's at the wrong place. It's at the bottom end of the intensity spectrum. So what is the next step?
Shift by W over 2.
Shift. Oh, shit. Oh, dearie me. Whoops. Goodness me. It reminds me of the first edition of a very famous book that you might have come across, which I'm too humble to tell you who the author was, but in the first edition, it was all the proofreading was done manually with no spell checkers or whatever. And I was talking about shift registers. And the person who was doing the proofreading either changed it out of spite or didn't notice that there was a letter missing from shift registers. I won't tell you which letter, but so So we shift. The shift is W over 2. So what that's going to do is now going to shift this band to its right intensity range. And the final step is combine. So we have the original shift, which was A. We've got that one there. That's the first part, the lower part, which goes from 0 to W over 2. So that is going to be 0 to W over 2. And then we go to W. And that's going to look something like that. It goes to that point there. And this is A. And then B, which is what we've got up there. We add that on. It's now shifted by W over 2. So it goes from W over 2 to W. And it goes something like that. And we end up with the histogram equalized over 2 bands. In practice, you can go over 4 bands, 8 bands, as many bands as you like. Come an exam question, I would be very, very mean to set anything more complex than 2 bands. If I set so, having got the final histogram, what's the final step? The pixel update table. And what this is supposed to give you is a better quality of the overall image. Doing selective normalization, you can bring out more detail in certain regions, but this is supposed to give you, in the case of the picture of the guy with the computer, you wouldn't have the whiteout on the computer. You'd still have that, and you'd have the enhancement of the black region. So it's really normalization in bands. So get the two difference. Normalization is a simple one. It's just taking the lowest pixel to 0, the highest pixel to W, and proportionally in between. This is normalization in bands and combining them, and we get a more equalized histogram in terms of the populations. Of course, the more bands you use, you will get a situation where sometimes pixel intensities have to go between 2 bands to keep them equal. So that can still give some distortions in the image from an equal point of view. Right. So that's equalization. What have we got next? Right, now we want to talk about edge detection. And this is the most complex of image processing operations that I'm going to be dealing with, and it is a 2-window operator. So what we have is 2 windows. Operating off the same image. They go through a function, and that produces a pixel at the center. So start off with 1 pixel operators, then 2 pixel operators, then window operators, and now we've got 2 window operators. And the most common use of this is in edge detection. And edge detection is a difficult task. It's needed to locate regions in images. It's essential for understanding images. As humans, we can do it pretty well. And even the digital media people sometimes are quite good at edge detection because they can draw cartoons. And they can draw lines which separate regions of a face. And cartoons kind of look like humans. But at the pixel level, they're completely different. So let's have a look at some edge detection operations. Those are 4 algorithms that came from a paper. And of course, what it's doing, it's looking at edges at the local level. So we're getting all the textures coming through. I think A, B, and C were 3 standard methods, and there's about 100 different algorithms for edge detection around. This was a proposal for a new method. Now, personally, I don't think that's much better than the rest of them. And you can see part of the problems. I mean, in human beings, the nose is quite a prominent feature. And if you're looking for edges, which is differences of intensity, there isn't on the nose. Oh, we haven't got a corner here, it's the same color. But you have if this was painted the same color here, there's clearly a structural edge there. The color is exactly the same. And we're perceiving an edge. And if you were drawing a face, you would draw a line down there, a very prominent line, to indicate the nose. It's not there. So this is really a problem. Perception is something we haven't cracked yet, and getting that into algorithms is tricky. So those are the outputs of some of the better edge detectors. Why do we need edge detection now? Autonomous vehicles, they want to detect the line in the middle of the road. That's not too difficult. But when you're on a country road with a track and grass, that is a much more tricky edge to detect. But human beings can do it perfectly okay. If I add noise to the image, it gets even worse. There's a very noisy image. Oh, come on, focus. How many edges can you see in that? What is it? Oh, yes, you can see it. Describe that image to me.
Is it the moon?
No, in terms of shapes. Circles,
Circles,
squares.
squares.
The outer one is a square. I think I can see a circle within there. And I think I can find another circle within that. So we as humans could actually draw that as a square with 2 concentric circles in the middle. And that's pretty intelligent. What do edge detection algorithms do? Well, that's one example of an edging of that image. And that just doesn't make sense to me at all. Hasn't got it at all. And a couple of other algorithms. Slightly better. I mean, this one, the sort of square is sort of there, but also a lot of clutter in it. And maybe this one, there's a semblance of the circles, but you wouldn't say that was particularly successful. And the edge detection algorithms I'm going to look at today, they are basically, that's the best they can do. But we do have some ideas to do better. And if there's time, when I want to talk about texture recognition before we finish this course, I'll bring some data along, which is pretty impressive, recognizing edges within textures, which is some of the work that's gone on here with PhD students in the past. So that's the problem. How do we even get images like that from real images? So that's the next thing we're going to do. It's pretty well up to the hour now, so can we have 10 minutes break, and then I'll carry on afterwards. Okay.
So, could you go back to one of the early pages on high-pass filtering, please?
Yeah, sure. got one?
The one after that, please.
Pixel update. Brad,
It was,
what's your problem?
it was on the first bit, there was the step-by-step bit. I only managed to get the first step before I went to the next page on. Yeah, it was
Yeah.
starting from there.
Obtain the histogram.
Yep.
Yep. Because of the coefficients in the high pass filter, we can theoretically go from minus 8W to plus 8W.
Yeah.
Right, we've got to normalize that to 0 to W.
Yeah.
Now, normally, a correction factor, which I think you suggested, plus 8W divided by 16 would do that.
Yeah.
But what it's going to do is it's going to compress all the valuable picture information to a very small band. And the quality of the image is not going to be, because you're using these limits. And in a way, these limits are meaningless. And there's the two examples of getting those limits to the pixel level. Most probably due to faulty pixels, CCD cells. So what you do, having got the histogram, you make a judgment as to what G min and G max is. And if this was a computer system, these could be two parameters you could vary and watch the image as you change them. A couple of controllers, up G min, up G max. But having established G min and G max, G min is most probably likely to be negative because 0 is somewhere in the middle. The first operation is to move G min to 0. Now, in this case, G min would be minus, so the equation what would it be? Aij plus G min. That would be the standard equation. If G min is minus, you are shifting it upwards. So that goes to 0. G max becomes G max minus G min. And if G min is negative, it's going to shoot over here. So we've then got the histogram between 0 and G max minus G min. So we're in known territory now. It's a normalization process. 0 is anchoring the bottom. We now got to have a multiply to take the top to W. And if the top value is G max minus G min, and it should be W, the multiplication factor is W divided by G max minus G min. So it really is the same as, it is standard normalization. The only confusing thing is we're going to get negative values.
Yeah.
Because of all the negative coefficients and the operator. Ooh. All right. Too easy? Yes. Project's finished. Project started.
Review done, but I've still got to familiarise myself with the software to run the simulations.
Yes, it seems like a good idea picking up software to run when you want to make changes and developing it. But, you know, what's up with pieces and what the software does?
Yeah. I've got a simulate power system increasing levels of concentration of renewable energy to see what's going to convert. I've got a model of recovery and it seems to work in the software. It's just I'm not exactly sure how to run the simulations and get it right and how to add and to subtract the infrastructure from the model.
You're not learning operating systems for computers. And you operate Windows, whatever the next one's going to be,
Yeah.
pretty well the same as the previous one, with some bits bolted on very carefully. But never tested.
Yeah, I've been getting things saying update to Windows 11, we guarantee it's good. Just like how they did from Windows 7 to Windows 10.
It's quite worrying actually, because we're still losing control of what's going on.
I would have been happy if we just stuck with Windows XP and kept it up to date.
And I've been reading that electric cars, the reliability has never been around for 3 years. The reliability is far worse than diesel. And the reliability comes from the software. You think when how often your computer has a glitch or your phone has a glitch.
The big problem with that is like mechanics that charge people a lot of money just to upgrade the software. Because most people are already getting subscriptions to software.
Why do they charge you so much? Pressing a button and putting
So they can get money.
oh, yeah, I like this game. As the engineers know, their time is up, so they're their last stand.
Yeah. Trying to ruin our reputation.
Right, guys. Oh no, that's a couple of minutes. What's the job market like? No. The job. Anybody got a job? You have? Wow. Good one?
Yeah.
Fantastic. I hope it's in engineering.
Because data scientist.
Oh, that's fair enough, yeah. So it's not politics or anything like that.
I'm honestly not sure what I'm going to go with, just something to do with power distribution or transmission.
Well, there should be power people. A really big problem with this power coming back.
I just don't want to get put into one of those companies that's like miles. Like if I get something like Scottish and Southern, I get rotated across it between Cornwall and Scotland. That's not going to be very fun.
You have to find the best of both locations and enjoy them.
Yeah.
Okay, guys, let's get going. Right, edge detection. It's been around for a long time. Let's just have a look back at what has been done in the past. It's a difficult task, although humans find it relatively easy to do, and it's a matter of finding boundaries of homogeneous regions from the background. Your face from the chairs, the trees from the skyline, whatever. Let's have a look at analog edge detection. Supposing I have an image, let's just go black and white. And the first half is black, and the second half is white. Now, in the old-fashioned television, historical television systems, you had a video signal, which was an analog waveform against time, which gave you the intensity of the image, the light coming from the image. And the analog signal from a system like this would be a waveform, which is V against distance, x. And as I scan the distance x across there, the signal may well have been something like this, till we get to that point there. And the signal will change from black, which presumably is a low voltage, to white, which will be a high voltage. Now, as you well know, although that looks like a step change, nothing in practice changes instantaneously. So the analog signal would be something that looks like this. It would go up, and it would go to the white level. And that's demonstrating the edge as a voltage against time. And if this is the edge, what do I have to do to that signal to find the edge? What mathematical operation can I apply to that voltage signal to get the edge, locate the edge? No.
Differentiate.
Differentiate. Give the man an apple, or the person an apple. So to get the edge, we would need to differentiate. So it's going to be dV by dx. Now, we don't know the equation of the video signal. It's random, it's not random, but it's hugely complicated, unpredictable. You'll never get the mathematical equation of that signal. So you've got to have electronic means of differentiating, which is a bit tricky, but you can do it with op amps. It tends to be sensitive to noise. And if I were to differentiate that, remember the differential is the slope or the gradient of the signal. And as I'm coming in here, 0. So we go along with the line that's in red. We go along there. And as we go up the change, the gradient from 0 starts to increase. And it gets to a maximum at that point there. And then it starts to slow down a bit and get less until it's 0 again. If that is the differential of that signal, that is the edge. Now, that's okay with old-fashioned television for the vertical edges, because the video scan would be horizontal. But what about horizontal edges? Old-fashioned TV cameras, scanning cameras. The only option you have is to use 2 cameras, one vertical and one horizontal, and synchronize the scans, which is messy and tricky, and it was a hell of a pain to try and get edge detection with analog signals. So, if I want to measure the gradient, supposing I have a pixel signal that looks like this, I'll just do one line. Supposing I've got 0, 0, 0, 0, 0, 15, 15, 15, 15. So it's going from black to white. What strategy could you use? And the guy who first thought about this was a guy called Roberts, hence the Roberts edge detector. Using that data and a little bit of arithmetic, how could you detect the edge, the rise from 0 to 15?
You just work out the difference between consecutive.
Yes. And let's take an operator of 3 pixels. And supposing this is minus, and this minus 1, keep that at 0, and that is plus 1. And what you're going to do is this is going to sit on the data. For example, sit there first of all. That's the pixel we're operating on. Is that an edge detection point? On an edge. Next pixel 0, subtract the previous pixel 0. No, it isn't. No, no. When we get to this position here, pixel ahead of the center, 15. Pixel trailing, 0, plus 15. It's a big magnitude. Something's going on there. Move the next stage, or 2 stages on. It would be sitting here. 15 minus 15, no. So what we would get if I applied this operator to this data would be a series of pixels. It would be 0, 0, 0, 15, 15, 0, 0. And there's your edge. And this was first proposed about 40, 50 years ago by a guy called Roberts. Get up there. And this would be the vertical edge detector. If I now want the horizontal, I've got the image digital as an array. Instead of scanning vertically, I could scan horizontally. So for the horizontal edge, we would use an operator that is vertical. And this could be +1, that could be 0, and that could be -1. And this would be the horizontal. Now, a lot of books just give them as a 3-pixel operator, but because we're used to 3x3 operators, I personally prefer to regard them as 3x3 operators. So my definition of the vertical would be a 3x3. So that is going to be the vertical, and it would be -1, +1, and all the others would be 0. And the horizontal operator would be +1, -1, and again there will be 0s. So if you've got software for filtering, you can change the coefficients and you've got an edge detector. It just standardizes the definition of the operators. Right. I've got vertical and horizontal edges, but when I'm looking at pictures like this, it's an edge. It's an edge. I don't normally want to distinguish between vertical and horizontal. I'm certainly going to, where's my picture of the guys? Oh, where's it gone? Gosh, how can things disappear? Amazing. Never mind. Looking at face. Don't detect vertical edges, they're just edges. So if I've got V and H, how do I get the overall edge? I've got, if you like, a vertical component and a horizontal component. How would you combine them? With diagram. There is V and there is H, and I want E. Pythagoras. Yeah. Or vectorial combining. E squared equals V squared plus H squared. Or E is the square root of those two. And remember, we're dealing with images, so there's going to be 16 million operations, and we've got this square operation coming in here. So although that looks like a simple calculation, it is millions of clock time, millions of steps in a computer program. It's going to be slow. Think back to distance classifiers. Bit of revision coming in here. We could calculate distances using Euclidean distance. We had an approximation. Would anybody like to suggest an easier way of calculating the resolved edge strength? Think city block distance. E equals mod V plus mod H. Add the magnitude of the individual vectors. Right. So that gives us the ability to calculate an overall edge strength map. And I'll just give you an example. I'll go through an example of an edge detector in more detail for one of the other methods, which might be more useful for you in the future. So, the resulting output is a picture, and it could be an example. And I've got 4x4 here will do. You don't have to copy this down precisely, it's just an example. Supposing for the first operation of these two, I get an edge strength of 0. Then for the next position, it's going to be 5, 12, 15, 4, 15, 12, 7, 15, 4, 2, 4, and 12, 2, 1, 1. It's a picture. We wanted to locate an edge. So the final step is apply a threshold. And this can be difficult. It's a parameter which you might wish to adjust to get better quality edges through looking at it and adjusting the threshold. Would anybody like to suggest a threshold I could apply to that image that might give me something interesting? It's got to be between 0 and 15, that's the clue. Okay, give me a number. 8, 12. I'll go for 12. I'll go for 12. Applying the threshold, any pixel that is less than 12 is 0, any pixel that is greater than 12 is 1. And so we're going to get our 4 pixels. 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0. That's a pretty good choice of threshold. There is the edge going through the image there. So if you were displaying that, 1 would be white or 1 would be black, 0 could be white, or the inverse. So that is extracting the edge from the edge strength image. So that was the first primitive edge detector that I've come across. It's named after Roberts, the guy who first invented. And of course, looking at these coefficients, first of all, it's not taking into account the diagonals. And actually, if I applied a diagonal edge to this, both detectors would miss it. So the next step was, okay, can we take in the diagonal information? And that led us to a second edge detector, which was called a Pruitt. And the Pruitt edge detector again, I will draw it as a 3 by 3 with zeros. Some people leave out the 0 cells. 2 of them. And the EV, vertical edge, is going to be -1, -1, -1, 0, 0, 0, +1, +1, +1, +1, +1, +1. This is the horizontal. 0, 0, 0, -1, -1, -1. Now, don't worry about the signs. If you get the signs the wrong way round, supposing you label these positive and these negative, it would still detect the edges. So the relative position of the pluses and minuses don't matter. They've all got to be the same in the same column or the same row. It will only make a difference if you are using the individual edge strengths to calculate the direction of the edge, which you might want to do. And the direction of the edge would be that angle there, going back to the calculating the overall edge strength. And if I wanted to detect the angle, theta is going to be equal to tan to the -1 of V over H. Now, if I change the signs, this plus, this negative, or that one, the reference of the angle would be different. It wouldn't be with the horizontal, it could be with the vertical. That would move. But the edge calculation would still reveal the edges. So that is the Pruitt. I don't want to say too much about that. It's the same operation. Take the image, correlate it with this. It will give you an edge strength for the verticals. It will be 1 column and 1 row less than the original image. Same with the EH. Combine the two, either square root of the square of the two, or add the modulus. Apply the threshold and see if the resulting edge is any good. Now, the one I'm going to spend a bit more time on, nudge, nudge, wink, wink, is the Sobel. And the Sobel operators is one step more. It's putting a weighting on the horizontal and vertical pixels, which is greater than the diagonal. Exactly the same thing as we had with the high-pass filter, going from the simple one to the Laplacian. And the code for the windows for the Sobel, for EV, is going to be -1, -2, -1, +1, +2, +1, 0, 0, 0, and the horizontal is going to be EH, and that is going to be +1, +2, +1, 0, 0, 0, -1, -2, -1. Right, we will do an example with the Sobel. Let's move that over there. And the image I'm going to take is going to be a 5 by 5 image. There we are. And let's put in 0, 0, 0, 0, 15. 0, 0, 0, 15, 15, 0, 0, 15, 15, 15, 0, 15, 15, 15, 15, and 15, 15, 15, 15, and 15. 5 by 5 image. What does that look like? Sorry?
Diagonal.
Diagonal, yeah. Top left is what color? Or what? Black. So that is the image of this picture, the digitized image of. It's going to be that. Right. EV, first of all. We're going to correlate, and let's put the window over here. It is going to be -1, -2, -1, +1, +2, +1, 0 in the middle. The first position of that window on our image will be there. That will produce a 3 by 3 output image. And what is EV for the correlation of that window with the red region of the image? Okay, -1 times 0 plus -2 times 0 plus -1 times 0 plus +1 times 0 plus 0 times +2 plus 1 times 15. 15. Move the image 1 pixel to the right. What's it going to be? 40.
Yeah, 45.
Right. Okay. It's now sitting here. It's going to be 0, 0, 0. It is going to be 1 times 0 2 times 15 is 30. 1 times 15, 45. Yep. Move it to the right-hand side. It's going to be 15, 30. 15 and 30 is 45. 60 minus 15 is going to be 45, yes. Bring it down one row, middle row. It is going to be 45. Next position in the middle is going to be 45 again, is it?
Mhm.
Yes. Move it over here. It is going to be
15.
30, 60 minus 45 again. Oh, 15, did somebody say?
15.
Shucks, let's get the
Both
right.
sides cancel out except the 15 on the top.
It is going to be 15,
Plus 45.
45, 60, minus, that's right, minus
Yeah, 45.
45 is 15. Thank you. I thought there was too many 45s coming up. Now the bottom. It's going to be 60
45.
minus 15 is 45. Here it's going to be
15.
15, and the bottom one is going to be 0. Anybody lost there? Have I made a mistake? Amazing. Now we want EH. And EH is going to be +1, +2, +1, -1, -2, -1, and noughts in the middle. And now applying that to the same, we're now looking at the rows. The top one is going to be -15. Yes? This one is going to be nothing from the positives. To the bottom, it's going to be -15. Yeah?
Yes.
Move over, it's going to be -45.
5.
And over the far side, it is going to be
Minus
-60, -45 again. Right. Middle row. Naught on the pluses, it's going to be -45. In the middle, it is going to be
-45.
-45 again. Over the far side, it is going to be -15. And down the bottom, it is going to be -45, -15,
Zero.
and 0. Right. We now need E total. And let's use E equals mod EV plus mod EH. Because it's simpler, unless I tell you to use a Euclidean equation, KISS, keep it simple. Yep. So the overall edge strength is going to be, oh, there's my picture. And E total is going to be mod 15 minus 15 is 30. 45, 90, 90, 90, 90, boom, 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 30, and 90, 30, and 0. So that is my total edge strength. This is a simple example because the input image was a real black-white sharp edge. So now apply the threshold, which is bloody obvious in this case, isn't it? What threshold would you suggest, anybody? 90, give me another one. 30, give me another one. 50, 60, 65, loads of them. Go for 89, shall we? Or 90. So anything 90 or greater is 1, and anything less than 90 is 0, which will give me 0, 1, 1, 1, 1, 0, 1, 0. And there, ladies and gentlemen, is the edge which corresponds to that edge there. Right. Any questions on that? It's all pretty simple. Yes.
In the exam, we'd be given the threshold.
No.
So we can just choose it. Right?
It's image processing. There's no one correct answer. There's millions of image solutions that might be valid. Okay. Right, that's a relatively simple edge detection. This one's been around for a good many years now. I'll just mention one more edge detector, which I'm not going to go in detail because it's quite tricky. But that is the canny edge detector. And Canny was a PhD student at MIT quite a long time ago now, and he proposed this, and it's sort of taken the world by storm. And the Canny edge detector, it uses a much bigger window. And the window is a Gaussian operator. I can't draw it in 2 dimensions, but it's the equivalent of taking a vertical Gaussian like that, plus a horizontal Gaussian, which will be so yes. I won't attempt to draw them, but basically it takes this Gaussian, it will be an array of numbers similar to a high-pass filter. This would be maybe 16 by 16 pixels, so it's much bigger. And you apply the Gaussian to each pixel position, which will give you an edge strength. And to avoid the choice of a threshold, what you do is, having got the full edge strength, you actually do a gradient descent. You move through that image, moving to the highest value of the neighbors, and that traces out the edge. And that seems to work pretty well on real world data. Right. Okay, quite a lot of material now. I've got a quarter of an hour left. What shall I do? Oh yes, lead on to textures. Where these edge detectors all fall down is the situation like that, where we have very noisy data. It's trying to pick out the micro edges. It's missing the big edges. And one approach which one can overcome this is if I were to take a texture, I'll draw an artificial texture, but it could be grass versus gravel, occurs in the real world. That could be edge detection of a track. But if I were to take an image that looks like this, deliberately shaded that way, and deliberately shading this way, I would say that image, where is the edge in that image? The edge is between the two textures coming down there. If that was input to a standard edge detector, the image would hardly change. If it's a good edge detector, Sobel, it would produce all the internal edges as well as the perceived edge you're getting. Now, textures are millions of them. You can't predefine what a texture is, but any suggestions on how we might do that? Given that this course is intelligent systems, it's to do with learning systems. Well, how about taking a window operator, sampling the image, move that within the same texture up to this boundary, extracting 10, 100, 1,000 images of that texture, use that as a training set for a neural network to learn that sloping texture. If we can learn that texture, we make a damn good chance of doing so. How can we use that as an edge detector? Well, you then release it on a different region of the texture. What will happen as we move across the texture, when it's in the region that it is recognizing this texture, it will give a high response. When it moves to a different texture, the response will come down. Having got that, differentiate the response, we've got the edge. And that is, I'll bring some results along on the texture stuff. That gives some pretty impressive edge detection. So, any questions? I've got 10 minutes left. Do you want to go into seminar mode for 10 minutes? Or do you want an early coffee? Any questions so far? Anybody looked at past papers yet? Good, aren't they?
I mean, the Sobel one was in the 2019.
Was it? Oh, we did some question spotting. Oh, dear, dear, dear. We will tell you the main topics of the 4 questions before the exam. That doesn't mean to say you ignore the others, because it could be subsidiary information you use. And you've got to answer 2 of Tatiana's questions, as well as 2 of mine. Which is a really bad way of doing it, because previously everybody used to answer Tatiana's questions and none of mine, and I didn't have much marking to do. Okay. How do you calculate the generalization set of a digital neural network with an output threshold of the maximum and generalization? No. What is a digital neural network? What is an analog? McCulloch and Pitts, what's it doing? Actually, you've been using the McCulloch and Pitts ideas this morning. Well, even here in this example, the Sobel, getting that, you've used the McCulloch and Pitts equation. What have you done? If this was W, you are correlating that with that window. You are calculating the summation of W, I, and I is going between 1 and 9. So actually you used the McCulloch and Pitts principle there. The only difference is that when we're using a McCulloch and Pitts neuron to learn to recognize patterns, we don't know what the weights are. And we have to use a training procedure to arrive at those weights. But because we know what we're doing with image processing, We've derived it from approximation of the differential. We know what the weights are. So in a way, that McCulloch-Pitts strategy is sort of justified by what we do quite normally. What are we doing? We're multiplying -1 times 0. It's that equation. And we're adding them up. And don't tell me you've forgotten McCulloch-Pitts neuron. Okay, shape factor. What's a shape factor?
It's a way of describing.
Equation, please, equation. In words. Perimeter squared divided by area. So in that case, what is the shape factor of a perfect circle? No, normalized it is, but I didn't normalize it normally. Yeah, I'll give you 4 out of 10 for that in the exam. It could be a normalized shape factor. Why would it be 1 though? Because the circle is, as far as we know, the most compact shape we can have, and we're normalizing that to the lowest value. Shape factor is perimeter squared divided by area. So if you want to recognize a circle, any circle, there we've got circles, here we've got squares. If they were perfect circles and perfect squares, the shape factor of the circle would be perimeter squared over area, and that is going to be, the perimeter is 2 pi r, all squared, divided by area, which is pi r squared, which is 4 pi squared r squared, divided by pi r squared. The r squareds go, which is the size dependent, one of the pi's go, and we're left with 4 pi. Constant. So if they were perfect circles, boom, 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 they would all give the same shape factor. So you could separate your circles from your squares if they were mechanical parts. And that was slightly difficult because you had to use pi. But what is the shape factor of the square, side r?
16.
16. Oh, excellent. Anybody not see that? 16? Good. 16? Okay, let's have an early coffee. I will be lecturing again next week, and the next topic will be textures, trying to recognize textures. There are notes for it, yeah. No, I think it will be face to face here. Yeah, I shall be here next week. If this place is occupied, we'll go somewhere else.